Hi, and welcome to the Digital Information Unit of the CSP course. In this unit, we'll be learning about exactly how computers actually store and represent information digitally. So what is digital information? Well, computers don't really understand ideas or pictures or even text. Computers are all about numbers. When it comes down to it, computers really aren't all that smart. Computers are just very fast at doing simple mathematical operations. They can move numbers from box A to box B, they can add numbers together really quickly, subtract numbers really quickly, and they can do this at 1,000,000 times per second. So if we want computers to be able to work with pictures and text and the type of information that's useful to humans, we need to be able to break this information down into numbers, because numbers are what are useful for computers. So computers are all about numbers, but specifically computers are about binary numbers. And so binary numbers are numbers that only use the digits 0 and 1. And we'll be diving deeper into exactly how this is possible to represent a number with only zeros and ones later. But for now, just know that this is how computers are storing numbers at the very base level, is using only zeros and ones. So a big part of computer science is finding various ways to store information as numerical digits. Once we're able to find a good way to store information as digits, we now have digital information. And that's nice because then we can use computers to manipulate this digital information, store it, send it, etc. So to store and manipulate information with computers, we need to find a way to encode that information into numbers. And to do this, we attach meaning to these simple sequences of digits. That way, to the computer, they're just sequences of numbers, but to us, they actually have meaning. And we do this all the time. We see this in the real world. We attach meaning to numbers on fast food menus. You can go to a cashier and order a number 2, and you and the cashier both know you're not literally asking for a number 2, you're asking for a cheeseburger. So this is an example of encoding information. You're encoding fast food meals as numbers. We also do this with zip codes in the United States. So every state gets its own series of numbers that define exactly where in the country that zone is. This is a version of encoding. We are encoding the location as a zip code. We also encode information using characters in the real world. For example, every state in the country has its own 2-letter abbreviation. This is encoding the state location with only 2 letters. So if I'm writing a postcard to someone and I address it to MI, so someone reading the postcard will be able to know that this postcard is being sent to Michigan because I wrote MI. And it turns out humans are encoded as well. Every human has DNA that spells out the exact instructions for making every type of protein in your body. So at the very top level, we have a human. But really, a human can be broken down into several cells. And each of these cells have their own proteins. Now, how are these proteins made? Well, each protein is made up of a series of amino acids. And the exact sequence of amino acids that go into making a specific protein is encoded using DNA. So we can think of DNA as just a long string of characters, and the only characters we can choose from are G, C, T, and A. So this long string of G, C, T's, and A's actually encode the instructions for building our entire body. And at the physical level, it's actually a string of physical DNA. It's a string of chemicals that are encoded by G, C, T, and A. But we can really think of it, for our purposes, as just a sequence of characters. So if we have a long enough sequence of only 4 different characters, we can actually encode the entire human body. And this is pretty incredible, that this complicated system of the human body really boils down to this simple idea of just a massive string of only 4 different characters. And this brings up the idea of data abstraction. So data abstraction is the process of simplifying complicated data into manageable chunks. And when we do this, we build out these layers of abstraction. So digital data is represented by abstractions at different levels. In the human body example, the cells would be one layer of abstraction. The cells don't really have to worry about what's going on down at the DNA level. They only have to worry about how to interact with each other, and they have to worry about what proteins they're made of. At the protein level, the proteins don't really have to worry about what cells they're a part of. They just have to worry about exactly which amino acids build them. So these are the different layers of abstraction present in the human body. Now, what about with something that we represent in computers? Let's take a sentence, for example. So at the very top level, we have the sentence layer of abstraction. At this layer of abstraction, we see the sentence hi. And this sentence means something to us. It means a greeting, it means hello. But if we break down this sentence, we see that hi is really just made up of very simple things, which are characters, an H and an I. So this is the character level of abstraction. But these characters aren't actually what are stored in the computer. These characters need to be encoded as numerical data. So what we do is we attach a number to each of these characters. So 72 represents an H and 73 represents an I. Now, like we said, computers don't actually store these numbers, they store binary numbers. So we'll convert these numbers into their binary form using only zeros and ones. But it turns out even these binary numbers are not the lowest level of abstraction. There's actual physical hardware that are encoding these zeros and ones for permanent storage. And this could be a sequence of lights that are on or off. This could be bumps or valleys on the surface of a disk. This could even be literal holes punched in a piece of paper called a punch card. What's incredible is that no matter what the exact hardware implementation is, the software result is the same. You are still encoding the sentence hi. And when you're typing out these sentences and manipulating strings in your programs, you really don't need to worry about the fact that they're made up of binary at the lowest level. You don't have to worry about what kind of hardware is being used to represent that binary. This is what's nice about the layers of abstraction, is you abstract away these lower levels. And at these lower levels, this is a very simple idea. You have an on or off. All you have is two separate values. And from these very manageable chunks of data, on or off, or high or low, or whole or not whole, we're able to encode everything we would possibly want to encode by turning these simple values into numbers, into characters, into full ideas. So why is it important to be able to represent information digitally? Well, once information is in digital form, we can do a lot of cool things with it. We can easily manipulate data just by tweaking those numbers a little bit. So for example, we can add a filter to an image to make it darker or brighter, or we can remix a song by manipulating certain parts of the data stream that makes up the song. We can also use computers to examine and filter digital information to gain knowledge. So here we have a picture of what a self-driving car sees. So self-driving cars using cameras and radars, and it's using several different types of measuring devices to input information from the physical world. And once that is encoded as digital information, it can use software, it can use programs to actually predict things about the outside world. It can locate obstacles, it can predict where other cars are headed, where other people are headed. So this is a really incredible use of digital information. What's also nice is that once information is in digital form, we can easily store it with computers and we can load it up almost instantly. These days we have virtually instant access to photos, movies, statistics of any field. In fact, there is so much data in the world that if only Google's data was stored on physical punch cards on pieces of paper, those pieces of paper would be able to bury New England such that the city of Boston would be buried significantly deeper than the ice sheet during the last ice age. And lastly, we can easily send information if it's in digital form. If I'm on my cell phone and I want to type LOL to a friend, it's very easy for computers to break down that sentence into binary data, and then the hardware of my phone can spit out that binary data as a burst of radio waves, perhaps long waves for a 1 and short waves for a 0. Those waves are picked up by a cell tower, repeated across to more cell towers, and finally it gets to my friend's phone. It receives the binary message and then is able to use the same process to re-encode it back into text. So being able to break down information into numeric form is a very powerful tool that is a huge part of computer science. And that's what we'll be exploring in this unit.